Should we wait more or we can start? Okay, so this is the course Embedded System with ARM. So today we will cover only the basic things like what is a microprocessor, what is a microcontroller. It's a short lecture today of 30 to 45 minutes. From the next lecture onwards, we will cover the advanced things like ARM architecture and other things working with the ARM. So uh, shall I wait again? Shall I wait more or I can continue? The screen is visible and everything is audible, right?
हाँ जी भैया.
Fine, then I can start. Okay, so I'll be leading a course on embedded system design, focusing on practical examples using two main platforms, an ARM-based board and an Arduino Uno. We'll explore various aspects and emphasize hands-on design throughout the sessions. Before diving into the practical work, it's crucial to grasp the theoretical foundation and the purpose behind embedded system. The first lecture, Introduction to Embedded System, covers the need for embedded system, their key characteristics, and design options. In this course, we will delve into the essence of embedded system, exploring their fundamentals and typical applications. Additionally, we will examine the common subsystem found within embedded systems. So this is an online system, so don't hesitate to ask questions throughout the session. You can open your mic, on your mic, and ask the questions. Okay, don't hesitate. So today there is no prerequisite, but once we start coding, so a basic knowledge of either C or C++ will be necessary, and I am sure you all are acquainted with it. So let's acknowledge our fortunate timing. Growing up in the computing age, many of us have witnessed computers since birth. Yet it's important to note that the landscape uh, looked quite different 4 or 5 years ago. Electronics, computing systems, and low power devices have proliferated remarkably, witnessing numerous advancement over the years. If anyone have any doubt, please ask. So what I was talking about, that we are fortunate that we are brought up in a world where from the birth onwards we can see computers, laptops, systems. So the environment we are accustomed to is filled with computational devices scattered around us. Traditionally, our familiarity rested with conventional computers like desktop, laptops, and servers. Desktop served as our primary computing platforms, but the affordability of laptops have transitions into more prevalent tools. Additionally, the significance of mobile phones as a computing device is often underestimated. Means it have actually we use mobile phones initially for call, SMS, but now it can have different applications as well. The computational capability within today's mobile phones surpass the power of computers from I think 30 to 35 years ago by staggering 1 million times. So these are the one type of computations. We can see desktops, laptops, mobile phones. But what we are going to talk about is not about desktop, laptops, and these conventional devices. We will talking about a different class of devices, which we call as embedded system. So there is a another category of computing system that remain concealed from our view. While desktop, laptops, and mobile phones openly display their computing functions, other everyday appliances like refrigerators or air conditioning units don't outwardly resemble computing devices. Yet concealed within them lies a hidden computing brain. These hidden systems are abundant in our daily lives, seamlessly integrated into the environment they were designed for. These systems fall under the category known as embedded system. They are essentially computing systems tucked away within the environment they are designed for. Um, Consider an AC conditioning unit. It's meant to reside within a room. For the computing system inside the AC unit, that machine itself is its entire environment, isolated from interaction beyond its confines. These embedded systems are tasked with controlling the AC unit, interpreting the commands you input through the remote control, and executing various functions accordingly. They are designed to respond to these specific commands within the AC systems. So we are going to learn these systems we call as embedded system, which work exclusively within their environment. Is it fine up to this? So the idea of embedded system is clear. What is an embedded system? Okay, you'll understand more if we discuss the common features of embedded system. So common features in most embedded system include their specialized or single functional nature. For instance, the processor within an air conditioning unit is solely dedicated to ensuring the AC's proper functioning without engaging in other tasks like calculations or mathematics assistance. Embedded systems are highly specialized, right? Means it is for a particular task, a single task, executing a single program tailored for their intended application. They interact with their environment by receiving inputs. Uh, Consider the example we discussed. Consider an AC unit taking commands from a remote control or using internal sensors to gauge room temperature and humidity. Based on these inputs, the system optimizes the activation of various internal subsystems for optimal performance. Consider let's take one more example. Consider a refrigerator with control panels allowing temperature adjustment. An example how commands can be sent to its processor through the environment, prompting specific responses. This principle extends to various appliances like microwave ovens, washing machines, and air conditioning units, where user commands influence the embedded processor actions. So one feature is it is focused on a single task. If AC is there, it is focused to run the AC effectively. It's say under a missile or under a certain system. It is only for that system. So it is not a general computer like our laptop or desktop where we can run any program. It is very specific and avoid multitasking or extra functions. This is the first function of an embedded application or embedded system. Second thing is most embedded systems face a stringent limitation on cost, energy consumption, and form factor. The processor's cost must remain low for economic viability, while its energy consumption need to be minimal, whether powered by a source or battery, keeping it hidden from the user's energy concerns. Additionally, the form factor, especially in sleek appliances like modern AC units, demands processors that are compact and not bulky. as oversized components would affect the overall size and aesthetics of the system. Embedded system demand compactness without expanding the overall area significantly. They require characteristics like being low cost, energy efficient, small sized, relatively fast, and capable of real time responses. For instance, in an AC unit, if the room temperature rises unexpectedly, the system must promptly activate the compressor to cool the room, demonstrating its real time responsiveness to external inputs. Real-time operation in embedded system entails responding promptly to inputs within a specified time frame. And this time frame is different for different applications. Suppose you are making an embedded system, that the time frame should be within seconds. Or suppose you are making an embedded system where, okay, 1 or 2 minute delay is fine. So this time frame is different for different applications. These systems process inputs from the environment, executing computations with varying permissible delays depending on the specific application. So these are the common features of embedded system. It is single function and it have some constraint like small size, low cost, it should consume low energy, and the third is it should respond in real time. Now after going through the features, now I think we can understand the definition of an embedded system. So embedded system, it is a microcontroller based system that is designed to control a function or range of functions that is not meant to be programmed by the end user. So it is a microcontroller based. We will understand why it is a microcontroller based when we understand what is a microcontroller. So for now, just keep it as it is. So it's a microcontroller based system. So why microcontroller based? Because microcontroller utilize is low cost. If you see our conventional processor, which is inside your laptop or desktop, they are the price is quite high, while the microcontroller is low cost and the microcontrollers consume less power. So that's why the embedded system applications are microcontroller based. Second thing, the microcontroller, the entire CPU is one chip. We will explain this further when we cover the microcontroller. So the processor, memory, and IO ports all are inside a single chip. And we already discussed this, the feature of embedded system, that is fixed functionality. We have seen the example of an AC. The embedded system is meant for AC, then is it is required to do the functions just for the proper functioning of AC. It does not need to solve any mathematical problem or do any other task. So it is quite limited for fixed functionality, because if we include more and more function, we the cost will be high and the real time response will be high. The memory we have to give more. So the form factor means the size that will increase. So embedded system are small applications, and embedded systems are it is hidden inside the environment. So if you see a smart AC, there is a computer inside it, but it is hidden inside it. We cannot see it. So there are many applications where like you are making a you have made a line follower. So the line follower, the microcontroller is programmed so that the line follower works effectively, nothing else. So that is a embedded system. Limited user interaction means there are limited ports available for inputs. We cannot give so many ports to take input. Then there are software constraint. So once the designer, the engineer make a embedded system, the user cannot change the software. Suppose the like you have a smart fridge. So you cannot change the software in it. You have a smart AC, you cannot change the software in it. So, but occasionally updates can happen, but you cannot change the inside software in it. So, and it is not meant to be programmed by the end user. But as of now, there is no customization, software customization. But in future, there may be some smart embedded applications where the user can program it. Maybe in the future it can. So there are many applications of embedded systems. One thing is consumer appliances like refrigerators, washing machine, AC unit, cameras, etc. Then office equipments, printer, fax machine, photocopiers, scanners, biometric scanners, so many things. Then automotive applications like airbags, anti-lock braking. Means like if you are making a smart car, which can there is a GPS in it, there is an engine control in it. So there is a computer in it, but the computer is hidden inside the environment. And the other application is in communication devices like mobile phones, networks, switches, routers, Wi-Fi, hotspot telephones. Then in security systems, the automatic door locks, baggage screening, surveillance systems. Then comes the specialized systems like intelligent toilets. You can see what is intelligent toilets. You can search it on Google. So the automated user responsive features. So there are many applications of embedded system. It's limited by your imagination only. Whatever you can imagine, you can make it. Now, is everything fine up to it, or any doubt? Yes, no, any doubt?
We agree.
Okay, so moving forward, now we are designing an embedded system. So there are design considerations. What are the things that we need to consider? First thing is performance. Oh, okay. Before performance, one thing is whatever the task it is intended to perform, it should perform. Okay, means it is a suppose it's a line follower. So the task is that it will follow a certain path. That is the task it is made for. Okay, so there are so many devices which can perform that task, but who will do it better? So that is called performance, where we see the speed and efficiency. So the first design consideration is your performance should be high. You make an embedded system, so the performance should be high. Second is power consumption. As I earlier said, embedded systems are computers hidden inside a system. So the power is for that system. Your computer should consume less power. So power consumption is a big factor. Your embedded system should consume less power. Third is memory constraint. The memory is also very small in embedded system applications. So you have to manage. Then fourth is cost effectiveness. So whatever you are making, it is going into the market. If it is too, the price is too high, no one is going to buy it. So it should be cost effective. Fifth is real time constraint. So the embedded system should respond real time. As I said, the example of an AC, if the temperature rises, the AC should respond in real time. It cannot say that, okay, in half an hour, I will uh, lower down the temperature. No, it should respond in real time. Sixth thing is reliability. Seventh is size and form factor. So earlier we used to see a TV which is big. Now it is going smaller and smaller. So now everything is in small size. So sleek size. So you have to consider the size also. It should not be bulky. Then security considerations. Then there should be protective measures. Then there is a development time, means whatever the time is required for developing the that application, that system which you are making it. uh, the development time affect the market time. Market time means what is the time which is required to bring a tool or bring a system into the market. So if you are bringing something late in the market, this if you're bringing something late in the market, can you see my pointer? I'm drawing something. Yes, no. Can you see? I'm drawing something. Can you see it? Yes, no.
हाँ जी भैया दिख रहा
Okay, so suppose this is on x-axis, we can have time, on y-axis sales. So, see, whatever you're making, you're bringing it into the market. So it's a economic model. The economics model, suppose there are various models, we are approximating it like this. So this is the time it went into the market, and then the sale increases. At a time, there is a particular time the sales is maximum. After that, sale will decrease. Okay. Now, suppose I bring the thing into the market late. So if you produce the thing into market quite a late, then what will happen? Your sales, suppose this is the time you produce the thing into late, so it will happen like that. Okay. So originally the sales was the money you will get is the area under this curve, the upper curve. But due to the delay in producing the system inside the market, you are getting only this much. So that's a loss. And for calculation purpose, we can approximate it with a straight line, something like this. So this is the W, means the time window in which your sales are there. This is the maximum sales. Then there is a delay D. Then due to the delay, now approximate this duration is D. This is D. This is W. And suppose this height is also W. So you can find the area of this equilateral triangle, then find the area of this, and you can compute what is the loss you there has been happened. Okay. So these are the thing, and there should be interoperability. That means your device should be compatible with other systems. Now coming the important slides, these are just the introduction. So how computer work? Surely a computer system consists of a CPU that performs computation by fetching instructions from program memory and executing them while interacting with data stored in memory. It reads or writes data to the memory during execution. The system also interfaces with the outside world through input-output subsystems. This interaction isn't limited to human users. It could involve sensors detecting environment parameters like temperature or pressure as inputs and responding by controlling devices like heaters or compressors as output. So it fetches the instruction, execute it. Fine. Then this I have covered already during I think Pratham or Dvitiya, but this is very important. So I will going to cover it again. So classification of CPU architecture. Broadly, we can classify into two architecture. There are other architecture also, but broadly we can classify the into von Neumann and Harvard classes. Von Neumann has a single memory for both instructions and data, typical in most conventional computer systems. Harvard, however, uses two separate memories, one for program stored in RAM and another for data in RAM. Microcontrollers commonly follow this setup, utilizing distinct memories for instructions and data. So you can see also in this diagram. So the left one is von Neumann machine and the second is Harvard machine. So you can see, so this is the CPU and there is a single memory for data and code, data and the instructions. Like, and there is a bus. So the thing which connects the CPU and the memory or any two bodies, we call it bus. Bus means the connecting units. So you can see there is a single data bus and single address bus. Uh, do you know the data address? What does it mean? Anyone? Are you familiar with these terms, data, address, or you want me to explain this? Please respond. It's online. I cannot see your faces. Otherwise, I can know from your face whether you're understanding or not. So you have to respond. Whether are you comfortable with these terms, data, address?
बस बता दो भैया एक बार।
अच्छा ठीक है, तो देखो बस देखो ये सीपीयू है और मेमोरी है, तो ये दोनों एक दूसरे से जुड़े कैसे होंगे? सीपीयू से कुछ यहाँ पे जाना होगा और मेमोरी से कुछ जाना होगा, तो दो चीज हैं, एक दूसरे से जुड़ते कैसे हैं? तो जो जहां से चीजें ट्रांसफर होती हैं उसको हम बस बोलते हैं, एक वायर की तरह होता है, समझो बस मतलब वायर। तो जैसे इनपुट आउटपुट डिवाइसेस हैं, तो यहाँ पे कुछ पोर्ट होगा, ये आपका सीपीयू से जुड़ा होगा, तो किस चीज से जुड़ा होगा? तो माइक्रो कंट्रोलर के अंदर या माइक्रो प्रोसेसर किसी भी आर्किटेक्चर के अंदर जो लिंक होता है उनके बीच, जो जिसको हम कहते हैं इंटरकनेक्टिंग डिवाइसेस, जो इंटरकनेक्शन एक दूसरे को जोड़ते हैं, उसको हम बस बोलते हैं। तो अब बस जो है तीन तरीके के होते हैं मेजरली, डेटा बस, एड्रेस बस, कंट्रोल बस। तो डेटा और एड्रेस क्या होता है? एक हमारा ये एक मेमोरी हो गया, ये हमारा एक मेमोरी है, तो ऐसे इस तरह से मेमोरी बटी होती है, ठीक। तो इस चीज का कोई एड्रेस होगा, इसका एड्रेस होगा कुछ, इसका कुछ एड्रेस होगा, इसका कुछ एड्रेस होगा, ठीक। जैसे मान लो इसका एड्रेस है 0 0 0, फिर इसका है 0 0 1, फिर इसका है 0 1 0 0 1 1 0 0 1 0 1, और इसी तरह से ऐसे मेमोरी हो, ऐसे बहुत सारे होंगे, तो वो एड्रेस हो गया। डेटा मतलब इसके अंदर है क्या, वैल्यूज क्या स्टोर है, ठीक। तो ये हमारी मेमोरी हो गई। तो सीपीयू पहले एड्रेस भेजता है कि मान लो इसका ये वाला एड्रेस भेजा इसने कि हमको इस एड्रेस पे जो डेटा स्टोर है वो हमको चाहिए, तो यहाँ एड्रेस बस। तो हमारा जो ये जो है मान लो, हाँ अब हम बोलते हैं कि जैसे ये जो है 8 बिट का है या 16 बिट का है कोई माइक्रो कंट्रोलर, तो क्या बताते हैं, जैसे मान लो ये मेमोरी की साइज जो है 2 रेस टू 8 है, 2 रेस टू 8 बिट्स, सो इट मीन्स कि जो हमारा एड्रेस बस का साइज होगा वो 8 बिट होगा। तो एड्रेस मीन्स ये जो लोकेशन है उसका क्या एड्रेस है। जैसे मान लो एक इस 0 1 और यहाँ पे वैल्यू स्टोर है 5 6। तो सीपीयू को 6 चाहिए, तो एड्रेस बस में एड्रेस भेजेगा। एड्रेस क्या है इसका 1। यहाँ पे 1 आएगा और 1 यहाँ पे 1 एड्रेस पे क्या स्टोर है 6। तो 6 जो हो गया वो डेटा हो गया और 1 एड्रेस हो गया। ऐसे ही इसको अभी तो 2 बिट का बस देखा, ऐसा मान लो है। इसमें मान लो 4 लोकेशन है। अब यहाँ पे 4 लोकेशन है तो इसका एड्रेस हो गया 00011011। ठीक, ये एड्रेस हो गया। अब इसमें कुछ भी वैल्यूज है 56 ए 32 15 कुछ भी वैल्यूज है इसके अंदर, ये डेटा हो गया। और एड्रेस मीन्स कि मेमोरी के किस, जहां पे अब आइडेंटिफाई कैसे करेंगे कि कहाँ कौन सा डेटा हमको लेना है। ये तो हमारी मेमोरी हो गई, तो ये एड्रेस हो गया। सिंपल सा मान लो जैसे एक घर है उसके कई कमरे हैं, तो रूम नंबर ये, रूम नंबर वो, रूम नंबर वो, तो वो एड्रेस हो गया, ये डेटा हो गया। तो वॉन न्यूमन में, और ये एड्रेस बस जो होती है वो एड्रेस स्टोर करती है, मतलब एड्रेस यहाँ से वहां ले जाएगी और डेटा बस डेटा ले जाती है। ऐसे एक होती है कंट्रोल बस, वो इनेबल या इंटरप्ट, ये सब कंट्रोल इंस्ट्रक्शंस उसमें होते हैं। तो वॉन न्यूमन में हमारा एक सिंगल एड्रेस बस होता है और सिंगल डेटा बस होता है। तो जो हमारा डेटा है कोड, अब इसमें अंतर क्या है। हम्म, जैसे अभी मशीन लैंग्वेज पढ़ोगे तो उसमें कुछ कमांड्स होते हैं, जैसे मूव A, B। ठीक है, ये हमारा एक इंस्ट्रक्शन है। इंस्ट्रक्शन मतलब हम माइक्रो कंट्रोलर या माइक्रो प्रोसेसर को इंस्ट्रक्शन दे रहे हैं कि ये काम करो। मूव A, B का मतलब बी में जो वैल्यू है वो ए में स्टोर कर दो। ठीक, ये इसका काम हो गया। तो ये क्या हुआ, मूव A, B, ये इंस्ट्रक्शन कहीं तो स्टोर होगा। ठीक, तो ये इंस्ट्रक्शन हो गया। डेटा का मतलब बी के अंदर कोई डेटा का मतलब कोई वैल्यू, वो इंस्ट्रक्शन नहीं है, वो कोई वैल्यू है, जैसे 5 6, या मेमोरी में कुछ वैल्यूज ऐसे स्टोर हैं 2 1, ऐसे कुछ वैल्यूज, तो वो डेटा हो गए। इंस्ट्रक्शन का मतलब ये कमांड्स। ठीक, जैसे आप कोड लिखते हो तो वो जो कोड हो गया उसको हम इंस्ट्रक्शन कहते हैं। और जो हमारा डेटा होता है, डेटा मतलब कोई वैल्यूज, वो सब हमारा डेटा होता है। डेटा होता है। तो जो वॉन न्यूमन होता है उसमें सिंगल एड्रेस बस होता है और सिंगल डेटा बस होता है। तो यहाँ से सीपीयू को कोई, तो सीपीयू जब इंस्ट्रक्शन पहले फेच करेगा कैसे, ये एड्रेस यहाँ पे भेजेगा कि ये वाला एड्रेस है, यहाँ से इंस्ट्रक्शन लेके आओ। मेमोरी से हमको इंस्ट्रक्शन आएगा, फिर ये इंस्ट्रक्शन यहाँ पे एग्जीक्यूट होगा। अब इस इंस्ट्रक्शन के एग्जीक्यूट होने में किसी वैल्यू की जरूरत पड़ी, फिर उसके बाद क्या करेगा, उस डेटा का एड्रेस भेजेगा और यहाँ से वो डेटा लेके आएगा। मतलब सेम एड्रेस और डेटा में हो रहा है। बट हार्वर्ड में क्या होता है, हमारे पास दो डेटा बस हैं, ये दोनों, ये और ये हमारे पास दो डेटा बस हैं और हमारे पास ये दो इंस्ट्रक्शन बसेस हैं। तो अब क्या होगा, सीपीयू को कोई टास्क करना है तो पहले क्या करेगा कि यहां से एड्रेस भेजेगा, यहां से एड्रेस भेजेगा, एड्रेस आएगा, उस एड्रेस पे जो इंस्ट्रक्शन स्टोर होगा वो फेच होगा, फिर उसको एग्जीक्यूट करेगा। उस इंस्ट्रक्शन को एग्जीक्यूट करने में किसी डेटा की आवश्यकता होगी, तो क्या करेगा, उस डेटा जिस एड्रेस पे स्टोर है उसका एड्रेस यहाँ भेजेगा और वहां से वो डेटा हमारे पास आएगा और वो यहाँ पे फेच होगा। ठीक, और जो रिजल्ट आएगा उसको मान लो हमको मेमोरी में स्टोर करना है, तो यहाँ से स्टोर कर देगा। तो ये होती है दो हमारा हार्वर्ड और वॉन न्यूमैन में जो बेसिक डिफरेंसेस हैं। ठीक, वॉन न्यूमैन में हमारा डेटा और इंस्ट्रक्शन दोनों सिमिलर मेमोरी होता है, सिमिलर मेमोरी में स्टोर होता है, और कह सकते हैं कि डेटा और इंस्ट्रक्शन के लिए सेम बस होती है। हार्वर्ड में दोनों के लिए अलग अलग बस स्टोर होती है। ठीक, तो इससे फायदा क्या हुआ हार्वर्ड में कि यहाँ से हम जब इंस्ट्रक्शन को एग्जीक्यूट कर रहे हैं उतने में हम मतलब यहाँ से किसी इंस्ट्रक्शन को ले रहे हैं, तो यहाँ पे हम पैरेलल प्रोसेसिंग कर सकते हैं, यानी एक समय पे दो टास्क। तो एक टास्क का इंस्ट्रक्शन फेच हो रहा है, किसी दूसरे के लिए अगर किसी डेटा की जरूरत पड़ेगी तो यहाँ से हम उसका भी ले सकते हैं, बट यहाँ पे नहीं कर सकते थे। यहाँ पे एक टाइम पे एक ही चीज, या तो डेटा आएगा या तो इंस्ट्रक्शन आएगा, तो एक टाइम पे एक ही इंस्ट्रक्शन चलेगा। यहाँ पे हम कुछ पैरेलल प्रोसेसिंग टाइप कर सकते हैं जिसको पाइपलाइनिंग कहेंगे, जो आगे चल के सीखेंगे। तो ये हार्वर्ड मशीन की ये एक एडवांटेज हुआ। तो अभी क्लियर है या कुछ डाउट?
भैया प्रोग्राम मेमोरी कुछ बताना।
ठीक है, देखो प्रोग्राम मेमोरी मतलब, देखो हमारा जो इंस्ट्रक्शन है और डेटा है। इंस्ट्रक्शन का मतलब जैसे ये एग्जांपल दिया ना, मूव ए कॉमा बी, ये एक इंस्ट्रक्शन है, ये कुछ करने को बोल रहा है। डेटा मतलब कोई वैल्यूज से, कोई वैल्यू है 5 6 7 8 9 10, ठीक है। जैसे ए के अंदर क्या वैल्यू है, बी के अंदर क्या वैल्यू है, वो डेटा में यूज हुई। तो इंस्ट्रक्शंस और डेटा दोनों मेमोरी में स्टोर होते हैं। ये एक मेमोरी हो गई, इसके अंदर इंस्ट्रक्शंस स्टोर है। जब आप प्रोग्राम लिखते हो, कंपाइल करते हो, तो कंपाइल करने के बाद वो पूरा का पूरा कोड आपका प्रोग्राम मेमोरी में जाके स्टोर होता है। ठीक, अब एक ही जगह पे सारा प्रोग्राम नहीं होगा, ये ऐसे टुकड़ों में होता है। यहाँ पे थोड़ा सा पार्ट, नेक्स्ट इंस्ट्रक्शन यहाँ पे, नेक्स्ट इंस्ट्रक्शन यहाँ पे, नेक्स्ट इंस्ट्रक्शन यहाँ पे, ऐसे ऐसे स्टोर होता है। तो ये इंस्ट्रक्शन अगर इसमें स्टोर है तो इसको बोलेंगे प्रोग्राम मेमोरी। ऐसे ही एक होगा डेटा मेमोरी, यहाँ पे डेटा स्टोर है, वैल्यूज कुछ स्टोर है। ठीक, तो अब क्या हुआ, हमें सीपीयू क्या करेगा, पहले इंस्ट्रक्शन फेच करेगा। फेच मतलब लेना। तो वो क्या करेगा कि हमको जहां स्टार्टिंग से मान लो इंस्ट्रक्शन यहाँ पे है, ठीक, मान लो 2 नंबर को ऐड करना है, तो पहले हमने क्या लिखा, तो ठीक है, ठीक है, तो अब हम 2 नंबर को ऐड करना है, तो मूव ए कॉमा 5, ये हमारा एक इंस्ट्रक्शन हो गया। मूव बी कॉमा 2, ये दूसरा इंस्ट्रक्शन हो गया। तीसरा हो गया ऐड बी। ऐड बी मतलब ऐड ए प्लस बी, ऐड बी का मतलब ए प्लस बी करना। और मान लो जो सम आएगा वो किसी लोकेशन पे हमको स्टोर करना होगा, स्टोर करना होगा किसी लोकेशन, मान लो 7 2। ठीक है, अब इसी को, इस कोड को देखो, यहां से समझेंगे। ये पहला इंस्ट्रक्शन है, ये पहला इंस्ट्रक्शन है, ये तीसरा इंस्ट्रक्शन है, चौथा इंस्ट्रक्शन है। पहला दूसरा तीसरा चौथा इंस्ट्रक्शन है, इसको हमने प्रोग्रामर ने लिख दिया। फिर ये चीजें एक प्रोग्राम मेमोरी में स्टोर होती हैं। ये हो गई आपकी प्रोग्राम मेमोरी। ये प्रोग्राम मेमोरी है। तो ये वाला इंस्ट्रक्शंस यहाँ पे स्टोर होगा, ये वाला इंस्ट्रक्शंस यहाँ पे स्टोर होगा। इसके सिंटेक्स पे आप ध्यान मत दीजिए, वो हम आराम से पढ़ेंगे, आराम से, उसकी बात नहीं, बस ये समझो इंस्ट्रक्शन क्या होता है। ये वाला इंस्ट्रक्शन यहाँ पे स्टोर होगा, ये वाला इंस्ट्रक्शन यहाँ पे स्टोर होगा। अब ऐसे बस चार ही थोड़े होते हैं, मेमोरी पूरी बड़ी सी होती है। अब इसके कुछ एड्रेस होते हैं, मान लो इसका एड्रेस है 00, इसका एड्रेस है 011011। अब सीपीयू जो है पहले क्या करेगा, इंस्ट्रक्शन फेच करेगा। फेच करने का मतलब कि इंस्ट्रक्शन पहले अभी तो इंस्ट्रक्शन जो है हमारी वो मेमोरी में है, यहाँ पे मेमोरी में, ठीक है, दोनों साइड पे, दोनों एक साथ लेके चलते हैं, मॉर्निमन और हार्वर्ड दोनों केसेस में। यहाँ पे डेटा और कोड के लिए सेम मेमोरी है, यहाँ पे प्रोग्राम मेमोरी है। तो प्रोग्राम मेमोरी में हमारा इंस्ट्रक्शन है, इंस्ट्रक्शन यहाँ से सीपीयू में आने चाहिए। तो मेमोरी से कौन सा इंस्ट्रक्शन चाहिए, किस एड्रेस पे वो स्टोर है, वो यहाँ से इंस्ट्रक्शन बस से वो उसका एड्रेस भेजेगा। तो यहाँ से वो भेजेगा, यहाँ पे एड्रेस बस में क्या स्टोर हो जाएगा, 00, 2 बिट का एड्रेस बस है हमारा यहाँ पे। तो 00 यहाँ पे गया, इस यहाँ पे जो स्टोर है मूव A,5, वो चीज यहाँ से हमारा आया सीपीयू के पास, ठीक। एड्रेस बस से एड्रेस गया, डेटा बस से डेटा आया, ठीक। अब हमारे पास ये इंस्ट्रक्शन सीपीयू एग्जीक्यूट करेगा, एग्जीक्यूट करके क्या करेगा, ए रजिस्टर है, एक वेरिएबल की तरह भी समझो, रजिस्टर वगैरह आराम से समझेंगे। ए में 5 स्टोर किया, ठीक, इतना एग्जीक्यूट किया। उसके बाद नेक्स्ट इंस्ट्रक्शन क्या है, 01, वो इंस्ट्रक्शन फेच करेगा। फिर बी में 2 स्टोर करेगा और ए और बी को ऐड कर देगा। फिर जो रिजल्ट आएगा उसको 72 नंबर लोकेशन पे स्टोर करना है। तो ये 72 क्या है, अब हमारे पास एक डेटा मेमोरी होगी, उसमें कई सारे लोकेशन होंगे, उसी में से कोई एक लोकेशन है जिसका एड्रेस जो है वो 72 है, ठीक है, ये 72 है मानो, ये इसका लोकेशन 72 है। तो जो सम आया मतलब 5 2 7, अब यहाँ पे 7 स्टोर हो जाएगा। 7 हमारा डेटा हो गया, और 7 किस लोकेशन पे स्टोर है, 72। तो ये एड्रेस हो गया। तो हमारा जो डेटा होता है और इंस्ट्रक्शन होता है, कमांड होता है या कोड होता है, वो वॉन न्यूमन में एक ही मेमोरी में स्टोर होता है, सेम डेटा बस होता है, एड्रेस बस होता है। हार्वर्ड में हमारे पास एड्रेस बस दो होते हैं, एक प्रोग्राम मेमोरी के लिए, एक डेटा मेमोरी के लिए, और डेटा बस भी दो होते हैं, ठीक है। अभी समझ में आया क्या, कोई डाउट? हेलो, हाँ ना,
आ गया भैया।
ठीक है, ठीक है। नेक्स्ट थिंग इज, तो अभी हम समझते हैं कि माइक्रो प्रोसेसर, माइक्रो कंट्रोलर, ये सब क्या होता है। फर्स्ट थिंग इज माइक्रो प्रोसेसर। सो यू हैव सीन अ सीपीयू, the conventional CPU, like whatever it is in your desktop. The CPU is quite heavy, it's bulky. So like you have seen the conventional Pentium CPU, it have so many transistors, so many things. The entire CPU, if we fabricate on a single chip, that we call a microprocessor. So microprocessor means the entire CPU is fabricated on a single chip. So I'm repeating these things, microprocessor, microcontroller, because I have told these things, I think 2 3 times, but still we go into workshops, school workshop, and things things to the school kids. Last time someone messed things, microprocessor, microcontroller, he was confused. So again, I'm repeating. So microprocessor means the entire CPU is fabricated on a single chip. We call it as a microprocessor. So what a microprocessor consists of? It consists of registers. So registers are small memory units used for storing data temporarily. So it's a memory unit, but it is smaller. So this is a CPU. In the CPU, there are registers. This is a memory unit, but it is different from your main memory. Main memory is quite big and it is used to store things permanently or depends on things, but it is big. Its register is a small memory unit and this is slow. The memory unit, your main memory is slow, but registers are very fast. Fast means storing and retrieving the data is fast. When I say memory is slow, means storing and retrieving data from it is slow. Registers are very fast and they are smaller in size. 8-bit, like your main memory is 1 terabyte or 512 GB, the hard disk, or the main memory is 8 GB or 4 GB. In terms of gigabyte, very small, 8 bits, 16 bits, 32 bits, 64 bits. So these are the registers. So in the CPU, there are registers which are used to store some things temporarily. Like the example we have discussed in the previous slide, the register were A and B. A and B were registers. Then they have ALU, arithmetic logic unit, which does all the computations, both arithmetic and logical. So this is the ALU. Okay. Then there should be some mechanism to interface external devices. So suppose if you want to connect anything to it, so there should be a mechanism to connect. Like suppose you want to connect a sensor, so there should be a mechanism. Then of course the CU, the control unit. Control unit, you can call it as a brain of the system. It controls everything and there are some timers and all. So not in the microprocessor, timers are not there, I think. So microprocessor, these are the things: registers, ALU, and control unit. So this is a microprocessor. Here you can see the schematic. So what are the things? ALU, control unit, register array means a set of registers, so many registers, and these things are external. These things are not part of the microprocessors. We can connect it. The memory we can connect. Memory is not a part of a microprocessor. Input device, output device. So microprocessor means the entire CPU is fabricated on a single chip. Fine. Next thing is microcomputer. Microcomputer means the computer system built using a microprocessor. This is the acronym we are going to use for microprocessor. Microprocessor. So computer system built using a microprocessor. So here is a microprocessor. Then we interface external memory. We interface external I/O ports. So this thing is called a microcomputer. So here you can see the address bus, data bus, control bus. The CPU load the address on the address bus, then it fetches the instruction from the memory, then execute it, right? So there are address bus. So these units are connected together using buses. It is just like a wire, okay? So these are called buses. So microcomputer means a computer system built using a microprocessor where we attach the external memory, input I/O ports. So you can see it is complex. We have to interface a lot of things and obviously bulky and expensive. So I have told the features of embedded system. The embedded system should not be bulky and it should never be expensive. It should be cheap. So that's why we cannot use a microcomputer for embedded application. So the third thing is we have covered microprocessor, microcomputer. Third is microcontroller. In microcontroller, the entire computer is on a single chip. Microprocessor, the entire CPU is on a single chip. In microcontroller, the entire computer is on a single chip. So you can see this is a CPU, then oscillator, then bus control, IO port, serial port, so many things. There are so many things inside a single chip. In Arduino, you have seen the microcontroller. There is a single chip and all the circuits are embedded inside it, or uh, everything is inside it. So it operates on data that is fed through its. There are some 10 ports, serial ports, then parallel ports. We will cover these things in detail when we cover the specific microcontroller. So it has generally analog input pins. There are some input ports, timers, and other necessary, whatever the circuit necessary for it. All these circuits are built in into it. So this is the microcontroller. So you can see these are the examples of microcontroller. So this is the PIC 12F508. You can see the size. There is a coin here. This is not a microcontroller. This is a coin. You can compare the size of this microcontroller. Then this is PIC 16F84A. And this is PIC 16C72. Then this is a Motorola 68SC0F SC05B16 PIC. Then again a PIC microcontroller, and this is the Motorola microcontroller. So these are the different types of microcontroller. So you can see the size is quite small. This small chip is the entire computer on a single chip. The entire computer on a single chip. So these are the different types of microcontrollers. So now we are going to cover the difference, how a microcontroller is different from a PC. So I told you, so in the PC, the program is stored in the disk. Either it is hard disk or solid state drive, the SSD. Like in my computer, it is SSD. Some of you have laptop, which is hard disk. So the program is essentially stored into the disk or SSD. Here it is, the program is stored here. When you run it, this program is going to be, it went into your memory. This is 512 GB, the or 512 GB, or like in my laptop, it is 1 TB. Some many of you might have 512 gigabytes. Here the program is stored. When PC executes a program, the program is first loaded into an allocated section of memory. This is your memory. This memory could be 8 GB or 16 GB. So you can see the size here is bigger. So every 512 GB, 1 TB. So here every program is stored. When you execute a program, this program is transferred into the memory. Okay. Uh, so here it is, suppose 16 GB. So part by part program is loaded into it and executed. Okay. And there is a OS, like in our laptop we have a Windows, or there are other OS operating system. This OS handle all low level operations. Like suppose you connect any external devices, then there is a driver code which need to be run for smoothly running it. So the operating system handle these things. But when we come to a microcontroller, there is no disk. We cannot afford a hard disk or SSD. There is a single memory in our microcontroller. So the ROM, the read-only memory, which is on chip, means it is inside the chip. On chip means inside the chip. The on chip ROM stores the program. So in the microcontroller, the ROM, read-only memory, stores the program. So whenever there is power or we reset the microcontroller, or we give power to the microcontroller, whatever program is there in the ROM, that will be executed. Now, here in our PC, we can load any type of program because we have a big disk or SSD, 512 GB or 1 TB. But here we have a small memory. So the size of this memory defines the limit of the maximum size of application. So suppose there is an application whose size is bigger than this ROM. So you cannot run into this microcontroller. So the size of the ROM limits the maximum size of application. And there is no OS here. In your Arduino, there was not any operating system. The ARM based board, which we are going to learn further, there is no OS, no operating system. So the program which is there in the ROM is the only program which is running whenever you give power to the microcontroller board. Whatever program is inside the ROM, that will be running. So that's the difference between microcontroller and PC. Any doubt? Okay, so that's all for the day. Today we have covered only the basic things. In the next lecture, we will cover the architecture of ARM. ARM means Advanced RISC Machine. Then we will learn in the next lecture, we will cover the architecture. Then next to next, we will cover the instruction set, and then we will start the programming. So is there anyone having any doubt? Anyone having any doubt, you can ask. Otherwise, you can leave.